Running southwest along the border of Washington and Maryland, the New York Avenue Bridge over the Anacostia River was built in 1953 as part of the Baltimore-Washington Parkway project. This four-span bridge stretches 450 feet in length and carries 6 lanes of traffic over the Anacostia River. Originally, the bridge was constructed utilizing steel girders and reinforced concrete substructure elements. However, a major rehabilitation in 1983 changed the two approach spans to reinforced concrete girders. In 2021, the New York Avenue Bridge's deteriorating condition warranted another rehabilitation. As part of the overall rehabilitation process, the District Department of Transportation awarded T.Y. Lin the responsibility of investigating and assessing the bridge's structural condition and developing a rehabilitation plan. T.Y. Lin sought out VCS Engineering to join the project team to provide evaluation of the bridge's deterioration using non-destructive evaluation and materials testing. Based on the collected results, VCS would support T.Y. Lin in service life modeling and development of an effective and efficient rehabilitation. The VCS team employed several different investigation approaches to perform a complete corrosion and materials evaluation. VCS used ground-penetrating radar, also known as GPR, which is a quick and reliable non-destructive testing method used to locate steel reinforcement and identify its cover depth in concrete. Cover depth is an important factor in determining the service life of a reinforced concrete structure, as there is a direct correlation between cover depth and concrete durability. This relationship is exponential as a reduced cover depth allows contaminants and moisture to reach the embedded steel much faster, allowing the initiation of corrosion activity. Another non-destructive testing method called a corrosion potential survey was also performed. This testing method helps the VCS investigation team identify locations in the structure with a high probability of active corrosion, even when there are no external visual indicators. The test is conducted by measuring potential difference between the steel reinforcement and a reference electrode placed on the surface of the structure. This is repeated in specific locations to create a map of corrosion risk on the structure. The VCS team collected corrosion potential measurements on elements of the bridge, which included a pier, an abutment, and concrete girders. In the pier, corrosion activity was generally limited to the tidal region, which has the highest moisture exposure. Corrosion activity of the abutment was noticeable, showing signs of spalls and signs of moisture exposure due to expansion joints. The survey conducted on the girders determined them to be generally at low risk for active corrosion. Concrete resistivity testing, also known as electrical resistivity testing, is another non-destructive testing method the VCS team used to determine the quality of concrete by measuring how easily an electrical current can flow through it. In this testing method, a Wenner probe was used. The probe contains 4 evenly spaced electrodes, and when placed on the surface of the concrete, a small electrical current is passed through them. The VCS team can then calculate the concrete's resistivity by measuring the resistance to the current flow. The resistivity of concrete can provide important information about its strength, durability, and ability to resist corrosion. High resistivity indicates good quality concrete, while low resistivity may indicate the presence of cracks, voids, or other defects that could affect the structure's integrity. Apart from the non-destructive techniques, VCS also extracted concrete core samples to perform chloride concentration and carbonation depth testing and petrographic analysis. The engineers include tests like these to gain a thorough understanding of the structure's exposure to contamination. Concrete chloride concentration core samples were taken at various locations and depths throughout the bridge structure. These samples are sliced in half-inch depth increments and then pulverized into concrete powder. Identifying the concentration and distribution of chlorides in the concrete allows VCS engineers to determine the current risk for active corrosion and estimate the remaining service life. Carbonation is another contaminant that is critical to understand as it can cause corrosion in concrete even without the presence of chlorides. Carbonation can permeate through the concrete matrix and spread through cracks. Carbonation depth tests were completed on each extracted core to determine how deep carbonation has advanced into the concrete. In chloride-contaminated concrete, carbonation can work in tandem with chlorides to start corrosion earlier than either of them on their own. The VCS team can identify carbonation immediately on site by spraying an indicator solution onto the sampled cores. The indicator solution changes to a pink or purple color at a pH greater than 9.5, which indicates uncarbonated or alkaline concrete. If the solution is clear, this indicates carbonated concrete. If the carbonation depth reaches the depth of the reinforcement, then corrosion can initiate. Our team determined that corrosion was caused by penetration of chloride ions to the reinforcement depth rather than carbonation. Petrographic analysis provides detailed information regarding the types of aggregates and binder compositions and identifies if any deterioration processes are occurring in the concrete. It also describes the general properties and proportions of the concrete mixture used in the original construction. The results of the petrographic analysis are critical in understanding the overall condition of the concrete. This suite of testing methods is utilized by the engineers at VCS because it allows them to evaluate and design the best structural durability and corrosion mitigation solutions available. VCS uses the data collected during the field and laboratory to understand the current and future conditions of the structure. VCS not only identifies current deterioration and its causes, but also how this deterioration is going to progress in the future. By understanding future deterioration, a more effective and longer-lasting rehabilitation can be implemented. Based on the evaluation of the New York Ave Bridge, the VCS team recommended several options to the District Department of Transportation for repair for each affected bridge element that can extend the service life of the structure from 15 to well over 75 years. These options ranged from basic repairs, which only addressed visibly deteriorated concrete, to extensive rehabilitation and corrosion prevention methods, like the installation of galvanic anodes. VCS also works with the owner to evaluate each option based on cost and service life extension, with the aim to select the best option to meet the owner's needs. VCS Engineering is a provider of engineering consulting services specializing in the investigation, assessment, and cathodic protection design for reinforced concrete structures. We have offices in the US, Canada, UK, and the Middle East, and provide services globally.